Hope you had a good weekend. Things are sure going quickly. We're in our third week now, and I just wanted to kind of remind you of a couple of things about the schedule for this week. I know it's kind of small for those of you in the room over here. First of all, it's worth reminding you again that every time you visit the website, even if you hit the back button, just make sure you refresh the page so you get the most recent version. And that's just because Google allows you to stay logged in for a long period of time, and you may find that you're seeing sometimes not the most updated version of the website. So our goal for today and tomorrow is to talk about chapter 7. It's kind of the most ambitious chapter we've encountered yet. So we'll see if we can do everything I wanted to do in those 2 days, but we're going to try as best we can. There's some homework that I have, at least right now, due Friday in class, and we're going to take a break from talking about new material on Wednesday and Thursday's date. The only thing I have scheduled on here is that I would like to have this class time available for you to come in and work on your homework and ask questions about the problems, because you'll find that not only is it chapter 7 kinds of things that are on there, but it connects with the time dilation and length contraction. So it's pulling together a lot of stuff. And what I'm hoping is that after doing that chapter 7 homework, you feel more of a level of mastery over the length contraction, time dilation, and relativity of simultaneity, which is the subject of chapter 7. So we'll see how that goes these first 2 days, but that's the plan. And then starting Friday, we're going to take a little detour out of Merman. And this is just because in the philosophy class, and we've already seen this happening in the forums, people tend to start talking about curved spaces and curved space-times. The last time I taught the course, we did that at the end, and because things are so compressed, we probably wouldn't have gotten there this time. So I'm going to do kind of a short treatment of just discussing how to think about curved spaces and curved space-times, expanding universes and all that kind of stuff, and how curved space-time is able to replace the idea of gravity as a force. So we'll do that on Friday, probably more of it Monday. I'm not really sure how long that's going to take, but that's a little detour. And then while you're doing that, I'm going to have you reading some other chapters that in Merman that, since there's no reading for that detour, this chapter, you'll see that for tomorrow, where am I looking here? Read chapter 8, post by Thursday at 11:59 p.m. And that's because we're not covering any new material, but I just thought, do that reading. That's about stuff that we've, pulling together some remaining mysteries that we now are in a position to answer in chapter 8. And chapter 9 and 10, you're going to read over the weekend, and I've got to remind myself what chapter 9 and 10 are. In any case, it's something that we're going to cover very lightly. Oh yeah, it's a discussion we've really already had, which is on chapter 9 is entitled, Why He Says My Meter Stick Shrinks, Although I Know His Shrinks. That's a discussion we've been having, although Merman doesn't really address that till chapter 9. And then chapter 10 is the same thing for clocks. Why He Says My Clocks Go Slowly, Although I Know His Go Slowly. So I'm just going to have you kind of read those in the background, post on your, with reading questions, and then we certainly can discuss any issues that come up in class, but we'll be taking that little byway into gravity and curved spacetimes, and then we're going to go back into Merman and continue with the discussion of just special relativity, which is what we've been talking about, and head into the idea, toward the idea that nothing can travel faster than the speed of light. We've seen maybe a couple of hints of that so far, but no definite reasoning behind why a physical object couldn't get faster than the speed of light. So coming up are chapters that, deal with the idea of how you would naively think about going faster than the speed of light, like keep your thrusters on and keep going faster and faster, and what you'll see is that you asymptotically approach the speed of light. Or if you have a rocket and then you shoot a rocket at point C out in front of it, and it shoots a rocket at 0.9 C out in front of it, and it shoots a rocket at 0.9 C out in front of it. Each of those are only going to get closer and closer and closer to C as viewed by someone who is at rest with respect to the first rocket. So, you know, all those kinds of naive ways that we might think of trying to accelerate us in a continuous way past the speed of light don't work. All right. I also have the exams graded. You guys did very well. And I'll pass those back at the end. And if I forget at the end, please remind me. Sometimes I just get so excited about the material that I forget to go on and do it. All right. Again, my fancy new pointer is not working, so I'm going to sit over to the side here, and I apologize for those of you in the class. But that's so that I can use my laser pointer to point with on PowerPoint. Just to summarize what we did last time, or the last two times, we talked about Rule 3, which is called the length contraction. It says, relative to the normal way of measuring length where a meter stick is in front of you or any object, if it moves along the direction of its length, it shrinks by a factor of 1 over gamma, where gamma is computed the usual way. And remember, gamma is bigger than 1. So this L prime is the length as viewed from the frame where it's moving. L is the length it would have in its rest frame. And 1 over gamma is some number that's less than 1. We talked about how other objects besides meter sticks shrink when they move in different directions. And you kind of have to practice, I think, on the homework that's due tomorrow. Is that right, chapter 6? You have a stick figure that you're supposed to distort in a certain way. So it's a little bit easier than drawing something like this. And we also, I wanted to mention something where I noticed the title was not quite the right title. We talked about how if a traveler is going between Earth and a certain star, and Earth and that star were at rest with respect to each other. In other words, they're in the same IRF, so they're moving as a unit or sitting at rest as a unit. Then we could compare the distance between Earth and the star, or the two objects that are co-moving, you might say, as seen by the Earth IRF inhabitants or seen by the inhabitants that are traveling between them by using the length contraction. And the idea, the upshot of it was that the people who are moving between the one location and the other location are going to see the shorter distance. They're going to measure the shorter distance. I had that entitled something about finding the distance between two events, but we shouldn't really think of it as finding the distance between two events, in the sense that if B is present at, you know, the event that you might be described as B leaves Earth, and B is also present at the event that might be described as B arrives at the star, what would B say for the distance that B sees between event 1 and event 2, those two events? In other words, if B had meter sticks stretched out and said, oh, okay, when I left Earth, Earth was at the 0 marking on my meter stick. And then I traveled, got to the star, and bringing my meter sticks with me, right? I get to the star and I measure the position of where that second event happened. It's going to happen at the same location, right? On my meter sticks. That doesn't mean other people are going to think it happened in the same location. But from my point of view, I'm just sitting there. I'm not doing the moving. The other stuff's going by me. And both of those events that we're talking about happened at the same place. So we would technically say here, B measures 0 distance between the event leaving leaving Earth and arriving at the star. What we're comparing here is the distance between these two objects that are in the same frame, and they may as well be connected by a rigid bar because they're never moving with respect to each other. They're only moving with respect to B in this case. So we can think of them like a rigid object. And so, of course, when we're looking at them from the frame where they're at rest, they have a longer distance between them. And when they're moving, that's B's point of view in this picture, they're shrunken, if you will, by a factor of 1 over gamma. Okay, last couple of comments, and then we're going to move on to chapter 7. This is something we saw before, and you guys already filled in this table with much effort right here. The idea I wanted to return to is that before we were advertising this as experimental evidence or confirmation for time dilation, it's also for length contraction, because notice we were able to back out the fact that if the muons assessed the distance from the upper atmosphere, in other words, we can think of from the muon point of view as they're screaming down towards Earth, they can feel like they're just sitting there. And what's happening? The upper atmosphere is rushing away and Earth is rushing toward it, but they're just sitting still, right? And they're seeing something that's moving by them at a very high speed, and they're going to see that as being not the same length as the rest length of the distance between the upper atmosphere and Earth. So we found just by backing it out and using distance equals speed times time that it had to be about 1/5 the distance if they measured that distance. But now we know we can see that directly, but from the length contraction, rather than sort of backing it out from the time dilation. So you can think of this as sort of experimental evidence also for the length contraction. They fit together. Finally, this slide just parallels a discussion we had for the time dilation and ways we talk about things. You know, there's nothing wrong with either of these statements. Fundamentally, it's just that you might kind of have the wrong idea when you state things this way. I might, you know, summarize the length contraction as moving meter sticks shrink along their length, maybe, or along the direction of motion. The problem that you might have in your head is this seems to suggest that the shrinking is some active effect on the part of the meter stick. The meter stick has to know how fast it's moving and shrinks. If you have that idea in your head, then that's certainly not right. They're not doing anything active because the meter stick, as far as it's concerned, is at rest in both cases, right? I mean, the meter stick, when it's flying by Earth, if you ride along with the meter stick, it still feels like it's at rest. That you might overcorrect and be overly cautious and say, well, moving meter sticks only appear to shrink. And that suggests, at least to my ear, that there's no real shrinking, and that the real length is the one as measured in the frame where it's at rest in front of you. And while that is an important reference frame, the normal way we measure things, it certainly is unnecessarily biased in favor of looking at things only from the point of view where they're not moving with respect to you. So here's a rather, again, very cumbersome way of stating it, but very precisely. I'm perfectly happy if you say in class, moving meter sticks shrink, as long as you aren't thinking that they have to actively do anything, because they have no idea that they're moving. The length of a meter stick is less when measured from an IRF in which it moves, compared to its length when measured from an IRF in which it is at rest. Or if you think about it carefully, if you're comparing its length with respect to two IRFs in which it's moving, the one where it moves more slowly is going to have the longer length. We have enough information to conclude that here. Okay, and that's the end, I believe, of our chapter 6 material. Can I answer any questions or any remaining nagging doubts about chapter 6? I tried to lay out chapter 5 and chapter 6 so they paralleled each other a lot, and so we saw a lot of the same analogies appearing, even though we went through it a little bit faster in chapter 6. Chapter 7, again, is going to probably be our biggest, toughest lift in this class in terms of technical material. At least it's one of them. The derivation is not going to be quite as straightforward as the derivation of the time dilation or length contraction, but that's okay. Every step is perfectly fathomable. It's just that there are more steps in the original derivation. Okay, so this chapter is going to demonstrate what Merman calls Rule 4, which is called by most people the relativity of simultaneity. And I am particularly labeling this as what Rule 4 tells us about is clock asynchronization. It tells us if viewed from the point of view where if I have clocks sitting in a certain IRF, well, we could certainly view those clocks from the point of view where they're at rest with respect to us. And in that point of view, it certainly makes sense for someone living in that IRF to want all of their clocks to be synchronized. So we'll assume that they're synchronized. If we look at two clocks that are separated when you look at them from the point of view where they rest by a distance L along the direction of the motion that we're about to consider, right? So in the rest frame, they're separated by a distance L, and then we have them viewed by someone who's moving with respect to that frame by a certain speed v along that L direction. Then we would find that the two clocks are no longer synchronized. So here I'm imagining here's a bunch of meter sticks stuck together. They're zooming by us. That's what this green arrow is suggesting here. And the two clocks are not synchronized as I'm watching them go by. Again, it's not me watching them. I have a whole bunch of fellow scientists in my IRF, and they're all taking just local measurements, so we don't have to wait for those photons or light pulses to get back to us and correct for them. It's much simpler just to have a whole bunch of people doing the measurements. And so it tells us how much off the one clock is going to be compared to the other one. So it's, in this case, it's saying, as you watch this thing go by, there's a front clock and a rear clock, and the rule is that the rear clock is ahead. Sometimes I summarize that as lagging clocks lead. In other words, the one that's further behind as it's passing by you is going to be ahead from your point of view, assuming it's synchronized in its own rest frame, assuming the two are. And the amount it leads by is L. L is that proper distance between these two clocks, measured when it's at rest, times v, the relative speed, divided by c squared. Okay, so that's where we're heading first, and it's going to take a little bit of effort here on our part, probably double the amount of effort of the previous two formulae we described. But again, you're not responsible for deriving this on exams or even really working it out much on homework stuff. We want to know how to use it. Okay, so we're going to imagine here, I'm imagining viewed from some inertial reference frame I'm going to call A. There's some clocks that are at rest with respect to each other. And of course, we're going to synchronize them in the frame in which they're not moving. That's the normal way we view clocks. So we're going to make sure that they have exactly the same time reading as assessed by what we normally mean by now. And we're going to imagine that they're separated by a length L. And I'm going to draw them as, you know, sort of being at two ends of a rigid bar. That's at least what I was trying to draw there. To suggest that they're not going to move with respect to each other. They're only going to move as part of a unit, right? They might be attached to your meter sticks that you're using in that frame. Okay, perfectly ordinary thing. But now we're going to view it from the point of view of someone else, inertial reference frame B. Okay, now to help us figure out what's going on, we're going to actually do a little experiment and use the constancy of the speed of light. Here's a light pulse that, you know, when the clock at one end of this reads time 0, we send a light pulse, and we're going to try to figure out what this clock reads when the light pulse gets down to the other end. Okay, and that's pretty easy to do in the other frame. So here I'm imagining, here's an earlier time shown up above. We're still in the A picture in both of these. So these are the A point of view, where A is at rest. Where the clocks are at rest. Pulse leaves here at speed c, it's a light pulse, and then it ends up over here. And the question is, you know, we're still not considering the point of view of B. Of course, B has moved along a little bit, but we don't really care about B yet. What should this clock read in terms of V and so on? Or sorry, not in terms of V, in terms of L, the relevant speed here is C. How could we calculate what time in terms of L and C that this clock should read over there? Given that we know how far it went and the speed it was going. L over C, that's right. That's just distance equals speed times time. The distance it went was L. The speed it's going is C, and T is that unknown time. So when we divide by that C, we get time L over C there. So this clock reads L over C in this little light pulse experiment. So these are two different times that I'm showing here. Photographs that were taken in reference frame A. Now there's nothing interesting yet, nothing complicated. Now we're going to take the point of view of IRF B and watch the same experiment being performed. So here, there's a couple things to realize. In B's point of view, that bar with the two clocks on it is moving to the left because B was moving to the right up above, right? from our point of view. That's if we rode along with B, we would see the bar going to the left. We're drawing this at an instant from B's point of view, where the light pulse is just leaving the clock on the leftmost side, right? And then at some later time, that light pulse is going to reach the clock at the right-hand side. And the question is, if we observe this, or the first question I want to ask is, if we observe this from the point of view of IRFB, what does this clock have to read when the light pulse arrives there? The answer is pretty simple. It's sort of a trick question almost, or not really. Yeah, and what would you cite to that thing that nobody can ever remember the name of, right? The principle of invariance of coincidences. There was a coincidence up here in the IRFA frame of the pulse arriving at the same location when the clock read L over C, and that coincidence has to happen in any other frame. You can't have the pulse arrive and it read a different time in a different frame. Otherwise, you could cause some, set up a situation where a catastrophe would happen, and then there would be a discrepancy between what the two found out. Okay, so this time over here has to read L over C. The question we're really after is this question mark up here. We're looking for, remember the rule we're trying to prove is, if we have two clocks that are synchronized and separated by a distance L in their rest frame, then when reviewed from a frame in which they're moving at a speed V, what's the degree of asynchronicity of these clocks? In other words, what's the reading going to be over here at this one? This one's going to read times 0, again, just by the principle of invariance of coincidences, because it did up here. It's got to read the same thing. Okay? I didn't even bother asking about that one, but the same thing applies to the claim that this reads times 0 when the pulse leaves. It's got to, because we already set it up there. So if we could answer what this question mark is, what's the reading up there, we would know the degree of asynchronization of those clocks in the frame in which it's moving. That's what rule 4, I think it was called, is endeavoring to do. Okay, so we've got a couple of steps we've got to move through. First of all, we're going to say, from the point of view of IRFB, we're going to call, so here's a photograph that happened. Here's a later photograph that was taken from the IRFB perspective. I want to call the time that elapses from the IRFB point of view between these two photographs delta t prime. We're going to have to argue a little bit about delta t prime. The first thing we're going to do to argue about it is, well, I've got to figure out what some distances are on here. Now, what I'm asking here in this blue circle is, what is this unknown distance right here? Now notice, at the earlier photograph, the left end of the stick was here with the clock, and at the later end, the stick was here. This is going at speed v, and the time that's elapsed is by definition delta t prime. So how can I write that distance in terms of delta t prime? Yeah, it's just going to be distance equals speed times time, and we don't know what delta t prime is, but I can write it in terms of that, right? This is v times delta t prime. How about this distance over here? We're going to use both of these. This one's important because, look, that's how far the light pulse had to travel between these two events, right? In this frame, the light pulse traveled this distance. If this is v times delta t prime and the whole length of this bar is L prime, we know it's shrunken in this frame, if you will. What does this have to read out to be here in terms of L prime and delta t prime? I think it's L prime minus v delta t prime, because when I add these two things up, notice when I add this thing to this thing, the minus and the plus cancel, and I'm just left with L prime. And that's what we want, right? The whole distance is supposed to be L prime. So we take L prime and we subtract off this amount, and what we're left with is this amount. That's what that formula says. Okay, we'll use those in a bit. Okay, our goal here is going to be to find out how much time elapses not in IRFB, would be what would be called delta t prime, but rather from the point of view of IRFA. Because remember, these clocks are ticking off in the usual way in IRFA. So if I could say, here's an event where this question mark is here. Here's another event, light pulse arrives at the rightmost clock. If we could figure out how much time A assesses between these two, then that would tell me the difference in the reading on the clock, because the clocks are operating in a normal way in IRFA. So if I knew how much time A assessed between this event and this event, then that I would be able to back out what this reading is, because I know if I knew how much time elapsed, this unknown reading plus that amount of time that elapsed should give me L over C. And so I can do a little subtraction and get out what that thing reads. And this is what we're after over here, is this question mark. So we're on our way to doing that. Now we have to be a little bit careful, because remember, we're not making any assumptions that these two clocks are synchronized. It's going to be different than the time reading difference between these two clocks, because I'm assuming this clock, we're going to show, in fact, this clock is not reading the same value in IRFB as the one that's a question mark there. So we really have to focus on these two clocks and figure out what that question mark clock is. Okay. Here's our two steps we're going to go through. The first is to find that time it takes the pulse to move between the two clocks in B in terms of L and V. We'll see how to do this, but we're going to focus on this experiment of the light pulse leaving the left end and arriving at the right end from the point of view of B, where this thing is moving. And then later on, we're going to relate that delta t prime to delta t that A would assess between these two events that we're showing right here. And that's going to lead us directly to the final question. So let's just focus on one right now. We're going to use these two distances we just worked on to find something about delta t prime. And delta t prime in this case, because this light pulse is traveling at speed c, again, by the same argument you've been giving me a couple of times, we can use distance equals speed times time. The distance it moved, isn't it, L prime minus v times delta t prime, right? That's the distance it moved. And that should be equal to c, the speed it's moving at, times delta t prime. And therefore, if I divide by c, that gives me an expression for delta t prime. Now, what I'm going to do, it sort of gives me an expression for delta t prime. What if I said, hey, I've solved this for delta t prime? Why might you take me to task for that? Here's an equation, and I know some of you are not used to seeing, if you're not math folks or physics folks, so many symbols in an equation. It can be kind of befuddling. But suppose I say, delta t prime's like my x that I'm trying to solve for. And you're teaching someone who's a first year in high school or maybe in 8th grade algebra, and you say, look, I've solved for x. Your teacher would probably say, no, that's not what we mean by I've solved for x. Even though you've got x equals on one side, why haven't I solved for delta t prime here? Yeah, there's another delta t prime. It would be like having the equation x equals x squared plus 3x plus 4 and saying, hey, I solved for x. Well, okay, what's the value then? I don't know, because I don't know what x is. But you've got it when you solve for a variable in something, you should really solve for the only appearance of that variable on one side of the equation. So that's an easy task to do here. We just got to disentangle this a little bit. In the meantime, what I'm going to do is use the fact that we know the relationship between L prime and L. This is a rigid rod whose rest length is L. The shrunken or length contracted length, L prime, can be written as the rest length times that factor 1 over gamma, which is the square root of 1 minus v squared over c squared. So I put that in there, and now I'm going to solve for delta t prime. And I can do that by, I don't know how much of this to show, but maybe if I just do one step here for the benefit of those who, what's happened to our, here we go. If, I've got to make sure I can see what the equation is here. we've got the equation delta t prime equals L times the square root of 1 minus v squared over c squared minus
Professor
v
Kelly,
times, yes.
would you mind setting like the boundaries of the
Oh,
board?
yes.
We're missing
Thank
a
you
little
so
bit
much.
of that.
I'm just going to move this over a little bit to start with. And
Thank
then,
you.
can you see it now?
Yes.
Yeah, that's a little bit better. I will mark the boundaries maybe when I'm busy with this. Okay. And then we had this divided by c. This whole thing was divided by c. If you divide a sum or a difference by c, you're certainly welcome to divide each of those things by c. And then the idea is I'm going to bring every instance of the variable over to the left-hand side. So here I've got something subtracted off over on the right-hand side. I'm just going to add it on to both sides. And when I add it onto this side, it will cancel out this one. And when I add it onto this one, I'm going to get delta t prime plus v over c times delta t prime. And that will be equal to what's left over here, which is L over c times the square root of 1 minus v squared over c squared. And if I go back and share my screen again, hopefully that's what we have. I didn't quite put all the steps in here. Well, that's almost what we have. And then I've got a common factor of delta t prime between these two. And so I factored out that common factor of delta t prime on the way to solving for delta t prime. So now if I wanted to get delta t prime equal, what do? I just divide by whatever this number is in parentheses on both sides, right? Oh, what have I done here? I guess I'm doing a little bit of extra gymnastics here. And that is, oh, you remember probably, at least you remember the words about something about a difference in squares formula and how it factors. So if you have a squared minus b squared, that's the same as a plus b times a minus b, both of those being in parentheses. So here I've got a difference in two squares. 1 squared minus v over c squared. That's the same as 1 plus v over c times 1 minus v over c. That's a factorization problem. Usually that's something everybody talks about and might even remember from high school algebra. That's just a replacement going there. And now I'm going to divide by this thing that's multiplying delta t prime, because my whole point was to get a formula for delta t prime. What happened there? Well, maybe we better flesh this out a little bit. So the formula that we had, again, let me move this over to make sure you guys can see what I'm doing. The formula we had is the one that I'm seeing up above, delta t prime times 1 plus v over c is equal to L over c times the square root of 1 plus v over c times 1 minus v over c. Now, this may be something you've forgotten, but if you take the square root of a product of two things, that's the same thing as the product of the individual square roots. So one thing I can do to this square root, like the square root of 3 times 5, is the same as the square root of 3 times the square root of 5. It's the same way with this product here. I can write this as the square root of the first one times the square root of the second one. And then we're going to divide both sides by this. So if I divide the left-hand side by this, it goes away. And if I divide the right-hand side by this, I could write it was 1 plus v over c. I could write 1 plus v over c. But I'm going to write that in sort of an unusual way. 1 plus v over c is the same thing as the square root of 1 plus v over c times the square root of 1 plus v over c. That seems like a crazy amount of extra work to go in, but why did I do that? So I could cancel out a common factor right here that appears in the numerator and denominator. And so our formula we end up with is delta t prime is equal to L over c times the square root of 1 minus v over c over 1 plus v over c. We don't need to think too hard about that formula. That's just an intermediate step for us here. So we're going to hold on to that formula. Any questions I can answer about the algebra if you're especially keen about it. I just want you to make sure you're seeing that each step is not horrendously complicated. It's using kind of high school algebra. So I'm going to hold on to that expression we got down here while we work on part 2 of our agenda. Part 2 was, well, look, I know something about delta t prime, but the claim is that the difference in these clock readings is what we would call the corresponding delta t. It's how much time elapses in A, because these clocks aren't running at the right rate in B. We don't want delta t prime. It doesn't tell us what the difference in readings are. But if I knew what A assessed as the difference in time between these two events, that's how much time elapses on these clock faces because they're behaving in a normal manner in A. Okay, so we are going to go back to when we're comparing time intervals between two events. Here's our events, event 1 and event 2. Event 1 is, well, it's sort of mysterious. It's in the B frame, when the pulse left the left clock, event 1 is what the right clock reads. Okay, and event 2 is what the right clock reads when the pulse arrives at the right clock. Okay, those are the two events. Pulse leaves left clock at the location of the right clock. What does it read? That's a certain event. So we've got a frame. I keep flipping back and forth between these, but notice that when we're talking about event 1 and event 2, they happen at the same location in A because that clock is at rest in A, right? It's just sitting there in A. And we know something from our time dilation work about when we have two events. Here was our event back we were talking about back in the day. Event 1, B leaves Earth. Event 2, B arrives at the star. And we said the important thing to disentangle this confusion about using the time dilation is that B's 1 clock was present at both events. And notice that that's true for these two events we're talking about now, but for A. In A, those two events, which are both at the location of the right clock, are at the same location in space. And so we can treat A just like we treated B's clock in this case. In other words, what we said was, oh, I remember, it's the one that's moving between the two events that experiences the less time, right? Whoever's moving between the two events, that was kind of the takeaway message from this. They experience less time between those two events. So that's A. A is going to
Professor Kelly, sorry,
Yes.
are you screen sharing right now? We're not.
Apparently not.
Oh, okay.
But now I am. Thank you for reminding me. Yeah, so the idea is I was just showing this slide that we did back in chapter 5 and reminding us of this situation. Thank you again for reminding me that where we had this person leaving Earth, that was event 1, and arriving at the star, that was event 2, and it was B who carried the same clock to those two event locations. In other words, the event occurred at the same location for B, told us our takeaway message was that B experienced less time between those two events. A, in this case, or the Earth frame is going to say more time elapsed while you were traveling to the star. Here it's sort of, at least in letters, the opposite. In this case, this clock is where event 1 happens and event 2 happens, and those clocks are at rest in what we're calling A, and therefore A should experience the shorter time between these two events, okay? So they happen at the same location in A, therefore A is going to experience the shorter time between the two events. And here's what the time dilation formula says, and we have to know how to interpret these symbols, but delta t prime is, well, delta t is the time difference in B between events 1 and 2. That's the larger time because B is the frame that's not present at those two events don't occur at the same location. So this is the larger time. And this is going to be, therefore, the corresponding amount of time difference in A between events 1 and 2, difference in clock readings. Okay, so the important thing is that this amount of time that A assesses is going to be greater than the amount of time that B assesses. This tells us the relationship between those two, and what we want is delta t. Okay, let me do a little work solving for delta t. The first thing I'm going to do to solve for delta t is bring this square root in the denominator, just multiply it up to the numerator on the left-hand side. And then I'm going to do the same trick I did before. Here, I switched the sides. I put the delta t was on the right-hand side. I just made that the left-hand side. I made the left-hand side the right-hand side. And then I used that trick that the difference of two squares could be written as 1 plus v over c times 1 minus v over c. And we're going to hold on to that formula for a minute. So hold on to that in your mind. It's solved for delta t, and that's what we're after in our part 2 of this agenda here. Okay, so going back here, well, we're concerned. One thing that, when I first started thinking about this confused me a lot is here's something labeled as event 1. And the question I wanted to ask is, where is event 1 pictured up here? And the answer is, it's certainly not this one, because that's reading the same size as this, but these aren't supposed to read the same time here. So this isn't event 1 being pictured in a different point of view. The answer is, it's not shown here. It's set yet a third time. I showed snapshots from the A point of view at 2 different times. Event 1, which is this question mark event here, that's happening at a time in between these times. So if you're looking for a picture of event 1 up there, it's not there, which makes our life a little bit difficult. But in any case, what I've done is extract that relationship between delta t and delta t prime. We've got something about delta t prime down here, and what we're going to do is just place in the expression for delta t prime that I've got in the box down here. And then I can do a little bit of simplification. What can I combine together? And you guys help me out, you algebra folks. We're almost there, I assure you. I know this is a little bit longer than the other ones, but I figured we should go through the logic even though you're not responsible for doing that. What can I cancel out here? Don't I have, when you have something just sitting around, that's the same as being an enumerator, right? So this square root of 1 plus v over c is in the numerator. And there's also a square root of 1 plus v over c in the denominator. Just like the square root of a product can be written as the product of the individual square roots, the square root of a ratio can be written as the ratio of the individual square roots. And then I can cancel out the square root of 1 plus v over c between the denominator and the numerator. What I'd be left with then is the square root of 1 minus v over c times another square root of 1 minus v over c. When you multiply the square roots together, you just get something that's not square rooted. Hey, that's kind of nice. A lot of garbage that we had in our intermediate formulae went away. So what it's telling me is that the difference in time in A, as A assesses the difference in time between these two events, is going to be how much time elapses between those two. And I know this one ends up at L over C, so we should be able to subtract and figure out what event 1's reading should be on that clock that functions normally in A. Okay, I just simplified a little bit more here by distributing. Okay, so let's go back and do that. So I'm asking the question here, what does this clock read down here at the lower left corner? We haven't labeled that one yet, but the idea is, since it started out at time t equals 0, and this is how much time elapsed from the point of view of A, that's going to be the difference in time between these two. In other words, we're calculating the difference in time in A between any two sort of analogous events here that are along this same diagonal point. We don't really need that. The important thing we're focusing on is what is the time here. We know that the difference in readings is L over C minus LV over C squared, and we end up at L over C. And so I'm just going to do that last step for us. Be on the board again, and let me move in some, sorry about that, fresh board space. So let's call this unknown amount of time on the right clock that's labeled as event 1. I'm just going to call that T1. What is that reading, T1? Well, apparently, if we add on to T1 the delta T that we found, which is L over C minus LV over C squared, we better get the reading on the clock at event 2, which we know is L over C. So what does that tell me that T1 has to be, the reading on the clock at event 1? Well, I can subtract that off both sides and it would go away. So I would get T1 minus this equals 0. And then I would add that onto both sides. That gives T1 equals LV over C squared. And that's the formula we were after. Okay, so this has to read LV over T squared. And so we've answered the question ignoring the second, photograph down here. If we just look at the first photograph in both of those cases, here we had in a rest frame where two clocks are at rest in an IRF and they're synchronized, separated by a distance L. Then we drew a corresponding set of clocks that were separated in time, sorry, not separated in time, but were riding along on a bar as it moves to the left in a length contracted way. I'm sorry, and I'm supposed to be sharing. That's what I'm hearing. Thank you. We were able to find out that this clock reading at this instant for IRFB, where this thing is zooming to the left, is advanced from this side. It's ahead of it by an amount LV over C squared. When this one reads 0, this one reads LV over C squared. So notice the takeaway. I said, if you're watching a train of clocks come towards you and pass by you, the ones that are farther behind in the rear of the train are going to lead. That's what we're finding out here. The clock that was behind in terms of passing you is actually ahead. So I sometimes say to myself, lagging clocks lead and leading clocks lag. I don't know why that's so memorable, but it's more memorable than lagging clocks lag, which would be exactly wrong. So you can think of it as just being the kind of opposite way. Okay, so again, you have to know something to apply this formula about what the situation is in the rest frame, and it tells you how to conclude about the difference in two clock readings in the moving frame, exactly how much they differ. And that's amazing that they do differ at all. In other words, what we're seeing at a certain instant, so here's a photograph in the A frame, right? It's an instant of time. That's not the same instant in time here, because if it were the same instant in time, these two clocks would read the same reading, but they don't. So we're seeing a whole bunch of different times down here compared to what we were seeing up there. That's going to take some unpacking. Okay? One way to think of it is we could have a bunch of events that were publicly identifiable, like little firecrackers going off. So here's a bunch of firecrackers going off as viewed by A. So here, imagine that all of these firecrackers go off simultaneously in A, right when all of A's, of course, synchronized clocks read 0, or they read noon or something like that, right? Qualitatively, the relativity of simultaneity is saying that events that happen simultaneously in one inertial reference frame happen at different times in another inertial reference frame. I say can because they will in the case where you're moving along the length of in which they're spread out in distance. Some happen earlier and some happen later. So here's the A view. It's just bang, they all go off at once, right, when the clocks read noon. What does the B view look like? Well, these simultaneous events happen at a bunch of different times over there, and so we've got to show a bunch of different frames to see all of them happen. So here, notice that in B's point of view, this rod that has a bunch of clocks embedded in it is moving to the left, right? If B is moving to the right from A's point of view, then from B's point of view, A is moving to the left, and these clocks are asynchronous. And notice the one at the rear relative to A is most ahead. I've tried to indicate that with little arrows on there, right? So this one's most ahead, this one a little bit behind it, a little bit behind it, a little bit behind it. Whenever, by the principle of invariance of coincidences, it's still got to be true that when a firecracker goes off adjacent to a clock, the clock better read 0. Because it happened in one frame. So it's got to happen in every frame because those were localized events. So when this one reads 0, that one goes off. Then a little bit later, when this one reads 0, this one goes off. Then a little bit later, when this one reads 0, this one goes off. and finally this one. So what happens as one big bang in one frame is boom, 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 down the line in a different frame. The relativity of simultaneity means what's assessed to be simultaneous events in one frame are not simultaneous in another frame. Okay? So again, that tells us how much the clocks are asynchronous by, but qualitatively it just means simultaneous in one frame is not simultaneous in another frame. And again, you don't really need the clocks there to tell us this qualitative kind of statement of it. If these are all simultaneous in one frame and I move along the direction which they're distributed in that frame, then from that rest frame, they're going to appear to happen at different times. And notice the spacings have changed too, because there's, spacings change between things when I move relative to them. In other words, I could have a firecracker go off over here, and then later on a firecracker go off over here. And I would say in my frame, they're spaced well, but somebody else might be present at both of them and say, no, they happened at the same place. So of course the spacings between them change too. I'm trying to show that by a slightly different spacing on here. Okay. That's not your reading response, so I'm not going to do that. And we're ready to do a worksheet just to practice with this initial form of the relativity of simultaneity. Any questions on that? Zoom folks, just jump in if you have a question. I'm going to pass out, while I'm hoping people are formulating their question, a worksheet. It's got two problems on it. We're only doing the first problem right now. This is what I sent out in email right before class started. So if you're on Zoom, you may not have checked your email, but you have an email from me that has this worksheet attached. And we're just doing the first page problem. It's got 3 pages on it, but we're going to do the other problem later. Mm-hmm. Mm-hmm. You're welcome. And I'm going to go ahead and put the Zoom folks into a breakout room. And I'll come check on you in a couple of minutes. I should say in this example, the clocks have been synchronized, of course, in their own rest frame, the usual way we synchronize clocks. So when you're on the train, we see the ones at the front and the back as being synchronized, but they're not going to be synchronized anymore as viewed by you when they're passing by. Okay, breakout rooms. So the answer to C, I will say, just think about it for a minute while the breakout room's closing, is not the same as the answer to B. That's the difference in the time of the clocks in the B at some instant. But then in C, we're asking, well, if one clock reads noon, and then we want to say, how long do we have to wait as this thing is going by for the second clock to read noon, when we start counting with the first clock reads noon? It's going to be different because there's a time dilation factor. Those clocks we're watching, we know it has to elapse by this much time, but we're watching a clock that's running slowly as we want it to elapse this much time, right? And so we have to use that time dilation factor, divide by the square root of 1 minus v squared over c squared. Okay, I think everyone's back in here now. So let me move this to the side, pin my video again. So any more questions on A or B before we move on to C? I was just saying to the class that who's here that the clock at, I'm sorry, when the answer to C is different than the answer to B. B is what's the difference in the clock readings. When one clock reads noon, what does the other clock read? As assessed by B, in which they're moving with respect to them. C is asking, from the point of view of someone standing on the ground where those clocks are moving by, how much time do we have to wait between the first clock reading noon and the second clock reading noon? And the answer is different. You guys can see this, right? The answer is different than this number because this is the difference in the clock reading. That's the difference in time that you might expect to be elapsed in A, but in the train's frame. But in the ground frame, that much time has to elapse and those clocks are running slowly. So we're going to have to wait a longer time for that amount of time to elapse when we're watching them go by on the ground. So this is C is going to be different than this answer to B. C is, we need to take that 6.6 times 10 to the minus 7 seconds and plug it into the time dilation formula. And remember, when you divide by the square root of 1 minus v squared over c squared, that makes it bigger, right? I'm multiplying by gamma. Gamma is going to be bigger than 1. So we're going to get a bigger time here. 1 minus, let's see, v over c in this case is 0.99. And that's 1 minus v over c squared. Okay, and when you calculate that number, you get a bigger number, 4.68 times 10 to the minus 6 seconds. Still not a big time, but it's bigger than the one we found before. Questions on that one? Notice I'm pulling together several effects, and we're going to have to get used to pulling these together, and that's part of what you're going to see in the Chapter 7 homework, which you'll be starting to work on this week, that you'll see all three effects coming together. If observers on the platform measure the length of the moving train, what do they find? 200 meters? Yes, it's length contracted, right? Which means it's going to be shorter than the 200 meters, which is the length in the rest frame. So we're starting with 200 meters. We know it's going to be shorter than that, and this factor will make it shorter, 1 minus 0.99 squared. Excuse me. And when we calculate that, we get 28.2 meters, according to my solutions here. Quite a bit shorter. Well, they're going very close to C, 0.99 C. I don't know what the gamma factor is. I didn't compute it here. And we used gamma a couple times, so it might have been worth our while to just compute gamma. But in this case, I'm multiplying by 1 over gamma, which is a small number. Finally, in E, this is the question I think Jesse was asking earlier. how far apart are the marks on the ground that were made in A? So in A, we're riding along with the train. I've got someone at the front of the train and the back of the train, and when their clocks, which of course are synchronized according to them, read noon, they mark with their chalk where the ground is under as the train is going by. They just make a little mark on the ground. And we want to know, as viewed by just someone measuring on the ground, right? So someone's there standing on the ground, how far apart are the chalk marks? You know, really naive, you might say 200 meters. And if you were a little bit less naive, you might say, well, we need to do a length contracted 200 meters. But that still would be wrong, because remember, as these things go by, those clocks aren't synchronized. The two people making the chalk marks are told to make their mark when the clock reads noon. The one in the rear of the train reads noon first, so they make their mark. There's already a distance of 200 meters between where that mark was made and the front of the train, but the front of the train's clock doesn't read noon yet. So the train keeps screaming along, and only later it reads noon, and then they make that mark over there. So we expect something bigger than 200 meters, but the question is exactly how much bigger. So, well, in this case, bigger than 28.2 meters, which is the length contracted version of it, right? If we assume this length contracted train, if we falsely assumed that the length contracted train, we would just see it marked like that, we'd be mistaken. No, the back gets marked first and the length contracted train moves along, and then the front gets marked. So in E, the calculation is not too hard, it's just thinking about it that's kind of hard. The distance between them is going to be 28.2 meters. That would be if they marked them simultaneously, plus how far the train moves in the amount of time we have to wait for the second one to read noon. And that's what we calculated up here. That's how long we have to wait between when the first one reads noon and when the second one reads noon. And in that time, we need to figure out how far the front of the train moved. Okay, so this distance we're going to calculate by using our good friend now, speed times time. The amount of time we had to wait, we calculated in c, and the speed the train is moving at is 0.99 c. So multiplying those together, 0.99 c times the time, well, let's put in c explicitly since nothing's going to cancel here. 0.99 c, c is 3 times 10 to the 8th meters per second. And the time we have to wait was exactly the answer to c. Okay, we have to fold all that stuff together, a big number, a small number, who knows what's going to happen. Plug it in your calculator, and you get something that's quite a large distance, 18 meters about. I rounded off some decimal places there. And most of that's coming just because they're not simultaneous, and so yeah, there was a little bit of displacement between the front and the back, but that wasn't the biggest effect. The biggest effect was, look, the back person marked first, and then the front kept going and going and going, and later on they marked it. That's amazing if you stop and think about it. You know, it may seem less amazing at the end of the derivation of the formula, but when you really just stop and think about how different that is from our everyday life, that when we're moving with respect to each other, events that are now for me, some of them are in your past and some of them may be in your future from your point of view. And we'll talk about that